share. All right. Deposition. Okay, this is the second part of film deposition. We have discussed a part of this content briefly. Okay, part of. So especially when we talk about CVD, when we talk about omnidirectionality versus unidirectionality of three different deposition processes, from evaporation, sputtering in the middle, and then CVD on the other side of the spectrum, right? So let's just, as usual, let's just recap on what we've learned in the previous topic. So let's go with the first question: why the vacuum level in the chamber is very critical for film deposition. Anyone? Why the vacuum level is very critical for film deposition? Anyone? Can we just go with any level of vacuum for deposition? Right, Sakina, how about you, Sakina? Why vacuum level is critical? You can unmute yourself, you can write down in the chat box as usual. Kenapa vacuum level penting? Sakina? So while waiting for Sakina, let's go to Mimi. Mimi, anything? Why vacuum level is important? Why does it have to be in the vacuum in the first place? Prevent contamination, all right? How do you prevent contamination? By having a vacuum. Macam mana boleh prevent contamination? Okay, you elaborate on that in the chat box. So while waiting for Mimi's elaboration, okay, any other point? Less ambient gas, okay, correct, less ambient gas can prevent contamination. Okay, any other reasons why vacuum? Arisha. Arisha, anything? Hadi? Why vacuum? Why specific vacuum level? Go. If you have less ambient gas, you have less contamination. And then what else? What else is the effect of less ambient gas in the chamber?
Sebab dia nak pressure 10 kuasa negatif 6 torr untuk produce medium quality film.
Ah, okay, good. To produce medium quality film. Thank you very much. Okay. To produce medium quality, or you can also push for high quality film with a low vacuum level. All right, thank you. Any other? Any other reason why do you have to have a specific vacuum level or within certain range of vacuum level? Haziq, tanya Haziq tu dia baru masuk ni. Haziq, kenapa kena ada vacuum level in the chamber for film deposition? Haziq, baru masuk dapat soalan.
Sorry doktor, saya tak dengar soalan ni.
Soalannya, kenapa you have to have a specific vacuum level in the chamber for film deposition?
So no contamination on deposition lah doktor.
Alright, no contamination. Sama macam Go, thank you. Sama macam Mimi tadi, right? Okay, good, thanks. Any other? Faris? Satu lagi ada, bukan satu lah, ada banyak tapi ada satu yang critical yang no one mentioned yet. Why do you have to have? Okay, all right. Let me see here. Yeah, improve the path length, right? So this is related to the MFP, remember? Mean free path. Kalau tak cukup vacuum level, then your mean free path will just be like 1 cm. 1 cm, yeah? Tak bagaimana pun, right? So you can cross-check with the summary table of vacuum level against mean free path, right? Okay, mean free path. Okay, Kavina said to form plasma. Yes. Kalau tak ada, if you don't reach certain vacuum level, you will not be able to form plasma because there are just so many things inside. So preventing plasma formation, right? So you need to have, so relating to the plasma, what is the typical base pressure that we use in order to form the plasma? At least, berapa kena ada? Kavina? What is the typical base pressure that we discuss for you to form plasma? So while waiting for Kavina, Juaria said reduce particle density so that mean free path for collision is long, thus preserving the energy of the particle. Yes, mean free path. Okay. So it's reciprocal to the vacuum level. Low vacuum, high mean free path. Low vacuum tu maksudnya negatif yang lagi tinggi lah. So low tu is a bit open-ended lah. Low tu mungkin tak berapa kuat vacuum, right? On the other hand, it can also be interpreted as negative, yang high negative, low juga, right? So you have to, when you say low, then you elaborate properly so that it's not misunderstood, right? So Arisha said low pressure plasma environment. Yes, low pressure plasma environment, just like what Kavina said. To form plasma, you need a certain level of vacuum. Right, Joanna said vacuum deposition typically requires vacuum better than 10 to the minus 4. Yep, mean free path. Yes, you have to have typically lower than 10 to the minus 4. So if you talk about a typical base pressure before you form plasma, we normally go down to 10 minus 5 at least. At least means 10 minus 5 or minus 6 or 7 or 8, right? Minus 4 boleh, but then it's not enough. It may also hinder plasma formation because the pressure is still relatively high for formation of plasma. So you need to have a typical base pressure of 10 minus 5. Remember, before you inject the argon gas into the system, you need to have a base pressure first. Mana kita kena vacuum dulu sampai 10 minus 5, but kemudian inject ataupun allow argon to come in, and then that will increase the pressure balik sebab gas masuk kan. So you are injecting particles, technically particles, into the chamber that will increase the overall pressure to in the range of millitorr, 10 minus 3 torr. So 10 minus 5 base pressure, inject jadi 10 minus 3, then plasma will form at that particular condition. Right. Question number 2, describe thermal evaporation process using relevant schematic. Ini you kena lukis lah. Go back to the schematic, describe the process, mention all the important parameters related to the process. Unidirectionality, kat mana source, kat mana target. And then if you talk about thermal, then you have to have resistive heating, you have to pass through current, and then tungsten boat, the precursor material has to be in tungsten boat, and then it will be melted, and then it will be evaporated, it will be condensed on the sample, giving you your intended film. Then mention the pressure as well. Lukis lah kalau ada soalan macam ni, then you have to draw or sketch your chamber and everything, the whole configuration of your thermal evaporation system. So the same goes to E-beam as well, right? The very same thing, except your source will be from the electron beam hitting the sample at 270, magnetic field, all the stuff. Then you get your evaporation. Soalan ketiga, describe RF sputtering process. Sama juga. It's just that this one is on the RF sputtering. So you have to be able to draw the chamber Make sure you know the connection, LC network, all those stuff, ARF, the frequency, okay? And then the target, the electrodes, the plasma, or the bias, if there is bias, the incoming line for your gas, right? How to solve process issues related to step coverage in evaporation and sputtering processes. Okay, I'll let you answer this. How do you solve process issues related to step coverage in evaporation and sputtering processes? Anyone? How do you solve step coverage problem? Any ideas? Let's hear from, hold on. Tanya Akilah lah, Akilah buat sputtering hari tu kan? Akilah, apa ni Izati lah, Izati ada. Izati pun ada. Kita dengar from Akilah Izati first. Soalan FYP Viva. Akilah Izati, how do we solve process issues related to step coverage? What do we do? Akilah Izati, what can we do to reduce? If you can't eliminate, how to reduce? At least. All right, so let me see. Izati, increase surface diffusivity. Okay, how? Yes, you can do that. How do you increase surface diffusivity of the sputtered material? You want to increase surface diffusivity while you're actually running the system? What do you do? What do you change? Or what do you introduce? Anybody else? Anybody else would like to add what can we do, or you want to elaborate on Izati's point? How do you increase? Yep. Go ahead. Izati pula. Haziq.
Saya ingat doktor ada cakap kita boleh apa? Rotate the substrate.
Okay. So rotate the substrate to improve uniformity, and that will partially address step coverage. Good. Thank you. Rotation. Rotation is one. Right. Any other? Any other points you can add on to Izati's point, or you can give other opinions on how to solve this? Kali, what can you do to solve step coverage? Step coverage will be very critical, especially if you're fabricating high-end devices, low technology nodes. Dia rapat-rapat, then the density of the features is very dense, so maknanya banyak features, and they are very close to each other, just like tall buildings, tall skyscrapers, dekat-dekat. Then kalau you nak buat deposition dekat in between tu, there'll be challenges on step coverage, shadowing effect. Okay, how do you ensure this issue is reduced or completely eliminated if possible? Mac, Mac, any idea? How do you solve this? Step coverage. One. Akilah tak cakap tadi, Akilah. Mana Akilah? Akilah tolong support Izati ya. How do you elaborate on that? How do you increase surface diffusivity of the sputtered particles ataupun evaporated particles? Any idea, Izati? Izati pula Akilah. How do you elaborate that point? Okay, while waiting for Akilah, let's hear from Alia. What else can you do? Alia? Ada ke Alia? time is it now? Oh, 10:25, right? So let's go for another 1-2 minutes, then we're gonna move on to the next one. Macam mana ni? Jadi rotation 1, increase surface diffusivity 2, but rotation. I want to hear something physical that you have to do that will lead to something else. Rotation, something physical lah. Macam kalau you are running the system, then what do you want to do? You can introduce rotation. Okay, so the same goes to Izati's point. What do you have to do what do you have to do physically on the system in order to increase surface diffusivity of the sputtered? Yes, exactly, good. Heat the wafer during and after the process. Good. You can heat the wafer, you can introduce substrate temperature. Okay, remember ada notation TS, so substrate temperature, temperature for substrate. So that means bila you say you are depositing ITO, for example. You're sputtering ITO on silicon, for example. Okay. Then while you're doing the sputtering, you are heating up the silicon substrate. Maknanya silicon tu dia panas lah, panas. Then bila you punya ITO is sputtered on the silicon, bila your ITO particles ataupun ITO atoms or molecules landed on the silicon, they don't just stay put, they tak land and stop. Okay, sebab dia ada surface diffusivity, sebab dia panas, so dia ada some some diffusivity or ada mobility lah, dia boleh bergerak, dia ada sebelum dia settle down, because you have heat factor on the surface of silicon or within the whole volume of silicon, right? So that can help minimize step coverage issue, right? So physically you can heat up or rotate. Alright, so okay, yang annealing process tu, well, you can say annealing as two things in this context. Satu is you can heat up the silicon while you're actually doing the sputtering. You can call that as annealing as well. Annealing ni dia punya theoretical definition ni adalah a high temperature process that you can do in order to reduce defects, eliminate defects. Okay, so that's typically related to annealing. So in this context, you can also call that as annealing, boleh juga. Or kalau you tak heat up the substrate during the sputtering, you can, after, just like the way you said, after the process, selepas you finish the sputtering, you can just bring the sample into annealing chamber, furnace, at some temperature, heat up for some time in nitrogen ambient, for example. So that is also annealing, right? So that can help improve step coverage, right? So that can be done. So if you are requested to give 2 points, then the 2 points will be rotation, 1, and introduce heating to the substrate during the process. Okay, so that can help introduce, that can help reduce step coverage issue, or in fact eliminate if possible. Okay, so good, done. So let's move on to our new topic, which is CVD. So as I said last time, when we talk about film deposition, they can be divided into PVD, category besar, PVD, physical vapor deposition, and then another big group is called CVD, chemical vapor deposition. And PVD can be divided into evaporation and sputtering. Evaporation can be divided into thermal and E-beam. Sputtering can be divided into DC and RF. Okay, nampak, kita dah habis the whole PVD. Now we're coming to the second category, which is called CVD, chemical vapor deposition. And in CVD, we have quite a long list of types for CVD. Tapi kita akan just go through the basic ones, because the whole idea of having different CVD is actually, if you follow the history, if you read the history, selalunya kalau researcher or scientist dia jumpa satu proses, they work on CVD, then dia jumpa satu proses, they modify, and they can see certain improvement in the film quality or in the device results, they coin that configuration as a new CVD. They are the first to coin. Dia yang bagi nama lah, more or less. Okay, dia jumpa tu convolution, also it works, then you call it something CVD, something else CVD. So that's why you can see so many different types of CVD. So this goes back to the literature. You have to understand why it was coined such a way, it was named such a way, right? So introduction to CVD, and then the processes involved, the steps involved in a typical CVD process, the growth regimes in CVD, CVD system, for example, AP CVD. AP is atmospheric pressure. So it can be done at atmospheric pressure, actually, not necessarily at vacuum, in vacuum condition. Atmospheric pressure, AP, ya, CVD itu sama ya, chemical vapor deposition, but AP is atmospheric pressure. So that means it can be done at atmospheric pressure. Okay, ambient pressure. LP, apa LP? Low pressure. Low pressure CVD. Apa PE? Anyone? Any idea? Plasma enhanced. Plasma enhanced CVD. Dia guna plasma lah, maksudnya plasma assisted. So, right? So, maksudnya you run your CVD, but then you have plasma to enhance the deposition rate and so on and so forth, and others. You have many more, right? Depending on the configuration of the CVD system. Okay, configuration akan determine the name of the CVD. Hot wire CVD is called HW CVD. Apa lagi ya? HFPE CVD, high frequency PE CVD. So you can see that tambah high frequency kat depan, HFPE CVD, PE CVD, AP CVD, what else? LA CVD, laser assisted CVD. Banyaklah, banyak. Here you see electron. So we'll cover the common ones only, but that doesn't mean those are the only type of CVD available. There are many more. Okay, mungkin ke depan pun akan ada different type of CVD invented or invented by researchers, right, after certain discoveries. So CVD, what is CVD? A firm deposition process which involves a chemical reaction, right? A firm deposition process which involves a chemical reaction. So this is the key, chemical reaction. So try to compare this with PVD, physical vapor deposition. This is chemical vapor deposition. So it's not physical but chemical. So that means it involves a chemical reaction. For example, you nak deposit silicon, right? So now let's recap while discussing this. So in this particular case, if you run a CVD process to deposit silicon, which involve a chemical reaction, what you have to do is you have to use silane. Okay, SiH4 is silane, silane gas. Silane gas ni very, very dangerous. Tapi ada dekat semua fab. If you run CVD silicon, then you have to have silane, no choice. Okay. Pernah jadi isu dulu, incident. Pernah ada incident dekat fab. Dekat Silterra ni, pernah dekat Infineon pun pernah. Silane punya incident. If you remember last time, if I'm not mistaken, I shared with you about NUS punya fire kan? I think, I'm not sure whether during this course or 386, National University of Singapore fire tu, ya tak? Yang building terbakar, and then it was shut down like half year or so, or 1 year perhaps. Oh, I think few years. Kot, sementara dia nak recover. The NUS fire was called by this. Yes, silane. Terbakar satu building. Solar Energy Research Institute of Singapore, SERIS Singapore. Shut down, habis. Okay, you can read online and research NUS fire due to silane. Okay, so it's due to silane gas. So if you run a CVD process to deposit silicon, you have to use silane. And what happens in the chemical reaction, you can see this, the silane is thermally decomposed. So the keyword here is thermally decomposed, or it involves thermal decomposition. So bila when you discuss about CVD, it always involves thermal decomposition. Okay, the conventional CVD. Kalau you pakai laser and whatever assisted tu, it's slightly different. But if you run just a pure conventional CVD process, it involves thermal decomposition. So in this case, the silent gas has to be thermally decomposed into silicon and hydrogen. Silicon Si plus 2H2, dual hydrogen. So this Si gives you the silicon thin film, and this hydrogen will be exhausted, akan di-remove from the system. Okay. So it involve a reactor. Perlu ada satu reactor, macam furnace pun boleh. So typically it's a big reactor, something like sputtering, but usually it's a bit bigger. Film formation involves 2 stages. To be able to deposit silicon, you have to have firstly gas phase mass transport of reactants. So in this case, you have to have the transport of silane into the chamber. Silane into the chamber. So if this is your chamber, so the chamber has to run at high temp, typically high temp, because you need to have thermal decomposition. So kalau you tak run at high temp, then there will not be any thermal decomposition. Sebab you nak pakai heat to decompose, heat to break down the gas. So then you have to have high heat, right? From the high temperature process. So then your gas will be coming in. So yang lain pun boleh guna juga if you want to. And then the second step will be surface chemical reaction. So the moment your gas is transported into the furnace at certain temperature, then there'll be chemical reactions on the surface of the substrate that will end up in the deposition of silicon by CVD process. Okay, so my question is, if you can relate to the previous topic, PVD, if you don't deposit your silicon by CVD, how would you deposit your silicon? If you can relate to the previous topic. Okay, you want to deposit silicon, but you are not allowed to use CVD. How would you deposit your silicon? Anyone? Macam mana nak deposit silicon? PVD, okay, you can use PVD. How? Which PVD? Aziz, nak pakai PVD mana? Aziz? Can use PVD, but which PVD and how? Elaborate sikit. Okay, evaporation, what do you want to evaporate? What do you evaporate?
Something like a compound for silicon.
Okay. You cannot evaporate compound, but you have to evaporate silicon punya element lah.
Oh.
Just silicon, not silicon whatever. Sebab kalau you evaporate compound, then you akan dapat compound lah. You want to deposit silicon, right? You want to get silicon on your substrate. So you then have to evaporate silicon, pure silicon. Okay, any other choice? Any other choices? Others? If you're not allowed to use CVD and evaporation, how else would you deposit silicon? Lain? Anyone? Syafiqah? Nak pakai CVD tak boleh. Nak pakai evaporation tak boleh. Apa lagi boleh guna? Soalan test ni macam ni lah. Soalan test ni style macam ni lah. If you're not allowed to use this, any other suggestion? Hadi? Hadi, you cannot use CVD, you cannot use evaporation. What would you do? Others? Okay. Right. Mimi? Sputtering, reactive sputtering because silicon is target. Okay. Sputtering, yes, you can use sputtering, but does it require reactive sputtering? Mimi? What is reactive sputtering? Well, why would you want to use reactive sputtering? You pakai silicon as your target, and then do you need any gas to deposit your film? No, right? So it's just a typical conventional sputtering process. No reactive sputtering required. Sputtering ni kalau nak form compound, okay? For example, if you have silicon, you nak deposit silicon nitride, then you inject nitrogen, then you get silicon nitride. Okay, combination of target plus gas, then that is reactive sputtering. So in this particular case, you can just use sputter target silicon. Pakai silicon sebagai target, you just sputter lah. Sputter to your substrate, and there you get your silicon, right? So sekarang you already know that if you want to deposit silicon, you can either go for evaporation, you can also go for sputtering, you can also go for CVD, right? For the same material. So maksudnya bila you belajar tiga-tiga ni, you can later evaluate if you have a material to be deposited as a film on your substrate, which process is feasible, which process do you want to go for and why, okay? So that's done. Let's move on to the next one, reactor type. It can be single wafer, it can be batch process. Typically, if you talk about mass production, then you have to go for batch process. Of course, there's no single wafer for mass production. Lab scale boleh lah. Kalau you run single wafer for mass production, you sengaja nak bankrupt lah. Right? Sengaja nak bankrupt. RF coil or furnace heater is used to heat wafers, so you need to have heating. You need to run the process at high temperature to induce thermal decomposition. Remember, the key is thermal decomposition. Nitrogen or argon may be used as carrier gas, right? So typical configuration macam di bawah ni. So what are the process parameters involved in a typical CVD process? Generally, there are a couple of factors, but there are more factors depending on which type of CVD you are using. Okay, typically the substrate temperature, the partial pressure of the gas, the total pressure, the gas flow, the time, the temperature, the configuration of the chamber, the wafer arrangement. Okay, yeah, right. Those factors will affect many things, and among the parameters in control are the growth rate, the thickness, uniformity, defects, okay, particles, and all stuff. So these are among the factors that you need to characterize after a CVD process or during the CVD process. Okay, growth rate you have to see during CVD lah. You have to monitor the growth over time, angstrom per second, angstrom per minute, nanometer per minute, micron per minute, whatever, depending on your intended thickness, right? So you can monitor that real time. So as a result, you'll get your film thickness. Growth rate leads to film thickness. And then your defect density is typically done or characterized or inspected after the CVD process, just like what we discussed in our previous processes. So tiap process you have to characterize next, and visual inspection is a compulsory step, right? It's a compulsory characterization that you have to do after every processing. After fabrication, you have to always do VI, visual inspection. Right. What are the steps involved in the CVD? So first one is the transport of reactants by forced convection to the deposition region. For example, if you talk about deposition of silicon, then you need to transport the silane gas. You need to transport the silane gas to the substrate. Masuk dalam furnace to be thermally decomposed to silicon and hydrogen. So that is the transport part. Transport of reactant by diffusion from the main gas stream through the boundary layer to the wafer. So ini dah sampai ke wafer. Sampai ke wafer, somewhere there. Previous step tadi mungkin kat belakang lah, baru nak masuk. Dan sekarang dia dah sampai kat surface. The third one is adsorption of reactants to the wafer surface. And they start to be deposited on the wafer surface. Then there'll be surface processes, including chemical decomposition reaction, thermally decompose the SiH4, surface migration to attachment site, minus your silicon will be landed or deposited at the right side, right side incorporation and other surface reactions. So this is where you get your film deposited. Kalau ni silicon contoh. If say you are depositing your silicon on quartz substrate, and this is your silicon. So this is what's happening at this step. Desorption of byproducts from the surface. This is where the byproducts, if you're talking about the reaction of silane, then we're talking about silicon plus 2H2. And your byproduct will be the hydrogen, right? Desorption means they are released from the surface. So due to thermal decomposition, they can break into silicon plus 2H2, and the 2H2 will be dissolved and eventually removed from the system. Transport of byproduct by diffusion through the boundary layer and back to the main gas stream. So dia keluar balik ke main gas stream and it will be exhausted. Akan kita exhaust off. Kita akan exhaustkan dia keluar. Every system you ada input and output. Input is your gas stream for the deposition, and then the byproduct will be removed guna exhaust. Transport byproduct by force convection away from the deposition region, right? Away, keluar daripada exhaust, keluar kot exhaust. So you can also represent these steps as this schematic. Okay, so gas stream coming, and then mass transport of reactant number 2, and then adsorption of reactants to the surface, start to be deposited, and then there'll be surface process, and they can start the reaction guys tu. Kemudian number 5, desorption of byproducts, hydrogen will be released. The gas phase mass transfer byproduct, removing the hydrogen, and then it will be exhausted. Okay, ini pun sama juga, the very same thing, except this shows a generic representation of the thermal decomposition. Okay, in our case, we've been talking about silane as the precursor gas, silicon as your solid to be deposited, film to be deposited, and your B2 here will be your hydrogen, right? So this is generic representation for all thermal decomposition processes involving all precursor material, thermally activated. So you have to have thermal decomposition. That's the key. Thermal decomposition. You have to use thermal, high temperature, to break the precursor gas into the intended material to be deposited. Right, in terms of the mass transport flux, so you can also represent this by this reaction. So this is your silicon wafer, for example. Wafer. Then your F1 will be the mass transport flux, F1 coming from silane, SiH4. Right, F2 will be the reaction flux, F2 reaction flux, because you want to deposit, right, you want to deposit your film, and then the reaction. Kita dah belajar sebelum ni, when we talk about deal growth. So batch process for polycrystalline amorphous silicon prefer to be in surface reaction regime, temperature wafers at the same temperature. Well, if you do the CVD process, okay, if you do the CVD, you can actually control, you can regulate, and regulate means control. Increase ke, decrease the temperature, and this will determine the quality of the final film. The quality here means the crystallinity. So you can either get amorphous silicon, okay, amorphous silicon. If you talk about silicon, you may also get a polycrystalline silicon. Polycrystalline silicon. Okay, so this one goes, you have to go back to the 386. Amorphous silicon, what does it mean? Polycrystalline, what does it mean? All the grain boundaries and stuff. In some condition, you may also produce monocrystalline silicon. if you talk about epi process, then you can actually get monocrystalline silicon, especially if you grow, say, you already have a silicon wafer, say 100 monocrystalline, right? And then you can run your CVD process to deposit thin film of silicon. Silicon juga, tapi thin film. For example, 50 nanometer, perhaps for specific purpose in the device fabrication. But you want that 50 nanometer to be monocrystalline. Boleh, that can be done because you can run that at a certain temperature, especially high temperature. And the crystallinity of the deposited layer, in this case, this layer, will take up the crystallinity of the substrate. Maknanya dia akan follow the crystallinity of your silicon wafer. In this case, P100 is monocrystalline. So as a result, the epi layer, the deposited layer here, by CVD at high temperature, will take up ataupun will emulate or will follow the crystallinity of the substrate, which is monocrystalline. So as a result, you can get 15 nanometer of monocrystalline silicon, right? So that can be done. So it's just about how do you regulate the temperature. So if you go for high temperature, it's a lot easier to get monocrystal whatever on whatever. So monocrystal silicon on silicon in this case. So maksudnya, you boleh je lah deposit silicon thin film on silicon wafer. It doesn't have to necessarily be any different layer on silicon. It can also be like silicon on silicon by CVD, okay, ataupun by evaporation, by sputtering on silicon juga, right? So you may wonder, kenapa nak deposit silicon thin film on silicon wafer? Kan wafer dah ada. Well, it depends on what do you want to get in your process, okay? What do you want to get in your device? Because you can also use, for example, your CVD to deposit amorphous silicon on monocrystalline silicon. You guna wafer yang sama juga. But then you can tune the process, usually low temperature, to deposit 50 nanometer of silicon, but that particular silicon can be amorphous silicon. Dia tak semestinya monocrystalline silicon or polycrystalline. So tengoklah nak apa. Kalau if you go for heterojunction, kalau if you talk about silicon solar cell, for example, specifically, if you talk about silicon solar cell, dia pakai silicon wafer monocrystalline P100. But then the solar cell itself is heterojunction. Heterojunction here means, kita dah belajar tu kan, 386 kan. Heterojunction means you are depositing another layer of different band gap, right? Different band gap. So maksudnya you can also deposit amorphous silicon on monocrystalline silicon. Right, so what's the band gap of amorphous silicon? Berapa band gap amorphous silicon? What's the band gap of monocrystalline silicon? Tulis kat chat box tu. Tulis monocrystalline silicon berapa band gap, amorphous silicon berapa band gap. They are both silicon, right? Same material but different band gap. So that's why we call them as heterojunction. Okay, anyone? Tulis kat situ. Berapa band gap monocrystalline? Berapa band gap amorphous silicon? One. Oh, almost 11. Okay, we're gonna stop soon. Okay, go amorphous silicon 1.75. Thank you. It's about 1.7 to 1.8 electron volts. On the other hand, monocrystalline silicon, berapa? Berapa silicon kita dah belajar 386 kan? We will learn on silicon. You can't afford to forget silicon band gap. Yes, thanks. 1.12 electron volt. Right? 1.125, 1.127. Lebih kurang tu lah. 1.12. Okay. So if you pair 1.12 monocrystalline silicon, this, and you pair it with amorphous silicon 1.75, 1.8, they are forming heterojunction, because walaupun they're silicon on silicon, but then if you talk about silicon on silicon, you have to be careful with the details of the crystallinity, because it could be amorphous silicon on monocrystalline silicon, and that forms heterojunction. Kalau you deposit monocrystalline silicon on monocrystalline silicon, 1.12 on 1.12, homojunction. Okay, so in this case, for silicon solar cell heterojunction, memang heterojunction based on amorphous silicon is intended, and it is deposited by CVD, and that will lead to, if you relate to the IV curve of solar cell, that will push the VOC of the device to higher side, the open circuit voltage. If you can relate that back to 386, okay? So a heterojunction solar cell is desired for high VOC devices, high VOC solar cells. So in this case, you need to use CVD to deposit amorphous silicon on monocrystalline silicon, but the amorphous and the monocrystalline will be of opposite polarity. So if you're talking about P-type wafer, then we're talking about N-type amorphous silicon. If we're talking about N-type wafer, then we're talking about P-type amorphous silicon, so that you have your PN junction, which is a solar cell, right? So this is how I want you to relate to the previous topic, to the previous course, okay? Belajar fabrication, tapi nak pakai proses apa depends on what do you want to fabricate eventually. So what process is the best in order for us to go there or to get our results, right? That's why it's very important to relate the fundamental in 386. Sebab tu subjek tu jadi prerequisite, okay? Kalau you tak belajar tu, then you are the missing piece in understanding. You know the process, but then you don't know the fundamentals. Nanti bila you nak relate the process to the fundamental, you will have missing pieces. Cerita tak habis. You nak explain pun tak sampai, right? So you dah cover dua-dua, then you know the fundamental, you know the process, then you combine both, and you decide what to use for your devices. Right. For epi growth, typically, if you want to get epi, so I say habiskan slide ni, then we stop for a few minutes. Epi, you want to get monocrystalline deposition. To be able to get monocrystalline, macam saya cakap ni, kalau you dapat mono on mono, it can be done, but you need high temperature process and you need slow growth rate. So your denominator per minute per second has to be low. You have to deposit at a very low rate, slow process, but that will ensure you to get monocrystalline quality. If you go faster, then you'll probably get polycrystalline or just amorphous. Okay, maknanya kalau you memang nak amorphous, you can just go as fast as possible because it doesn't compromise anything. But if you want to go mono, you cannot be so fast. Okay, cannot be so fast. So there are regions where you can just get polycrystalline. For example, if you go for low temperature, the temperature is on the inverse side. If you go to the right, it's actually low temperature because your axis here is inverse of temperature. If you go to the left, it's high temperature. High temperature, you're gonna get mono or epitaxial. If you go low temperature, you tend to get polycrystalline. If you go even lower, you will get amorphous silicon, right? So if you imagine in terms of temperature increase temperature of CVD, at low temperature, you're gonna get amorphous silicon. At medium temperature, you're gonna get polycrystalline, poly CSI. At a very high temperature in the region of 1000 over, you're gonna get monocrystalline. Okay, so using this understanding, you can then design your process temperature to be able to obtain certain qualities of your deposit layer. So we'll just stop here for a while. Then second half kita dah boleh habis. Second half we're gonna finish this the CVD, and then next week we're gonna start with process integration. I think by next week we can finish all the topics already, and then I will leave you with your assignment, with your presentation that will be given soon, right? So I'll just stop here for, right, what time is it now? 11, okay, June 11. So let's just stop now and come back at 11:10. Okay, 11:10 kita akan sambung ya. About 10 minutes break. Right, see you then, bye. All right, let's continue. Where was I? Participants. All right, can you see the slides on the screen? Okay, thanks. All right, so yeah, you can tailor your process to produce specific type of crystallinity. For example, if you talk about a low temperature process, then you will produce more of a silicon. And then if you go for medium temperature, you will get a polycrystalline, okay? And if you push for higher temperature process, then you'll get monocrystalline by epitaxial layer, okay? So these can actually be achieved based on what you want to get, right? Yeah, this is another thing that you can do, or you can play around. Temperature, the growth rate, for example, okay, with different incoming gases. Temperature against growth rate. So for example, if you talk about this structure, a cross-section doped epitaxial layer for bipolar transistors. Okay, bipolar transistors. So you can vary the doping, and well, we'll come back to this when we talk about process integration. Because this process has already, or no, this architecture or this device, if you like, has already combined a lot of serial steps, right? A couple of steps to be able to get this structure. Okay, if you talk about dope epitaxial silicon film, for example, then these are the gases involved: PCl3, arsine, phosphine, diabrane for doping, right? For deposition process. Okay, doping of silicon. So we have learned about doping into silicon for quite a bit. We've discussed in diffusion, we've discussed in ion implantation, and by now you already understand that if you want to dope silicon to make it N-type, you have to use group 15 atoms, for example, phosphorus, antimony, arsenic. If you want to go for P-type, then you have to use from group 13, like boron, aluminium, and gallium, for example. So those are the common ones. Assuming the host is silicon, the host atom is silicon, right? So in this particular case, you can have a look at this correlation or relationship between your indium, dopant concentration, not indium, dopant concentration in lon, right? And then same scale for the growth rate, right? So this one is the decomposition region, if you like. And then in this one, if you use arsine for your doping, and the partial pressure and whatnot, right? So when you run your diffusion, process, you want to incorporate your dopants into silicon. Okay, remember when you dope, you're actually incorporating foreign atoms. Incorporate. Let me just put as incorporate into silicon. So you introduce new atoms into silicon, but there are possibilities of, for example, out diffusion. Out diffusion maksudnya apa? Dia punya dopant tu keluar balik ya. You want to diffuse, but then you have out diffused your dopants from silicon, not into. Doping of the epitaxial film by solid state diffusion from the substrate. Okay, for example, you can dope in this case, you can use, you can extract the dopants from the substrate. For example, if you have silicon, for example, you have silicon. Say if you have silicon undoped, you deposit on glass, glass boleh juga. Glass, if you use BSG, borrow silicate glass, BSG. If you run this process at high temperature, then there are possibilities of out diffusing boron daripada glass masuk dalam silicon. That is also possible. So you are out diffusing borons. So boron is dopant kan into silicon. So that is also possible. So this is one example of out diffusion. Okay, one example of out diffusion. Banyak lagi lah. If you're working with firms, epitaxial film deposited on some other layers at certain temperature, that could induce out diffusion, typically high temperature. Okay, induce out diffusion, and then you will eventually have a change of your diffusion level or doping level in your epitaxial film. Okay, auto-doping is another scenario. Doping of the epitaxial film through the gas stream from the dopant evaporation from the wafer, front side, back side edges, or from other wafers. You auto-dope from different area. So you auto-dope. You don't want to dope, but then you auto-dope due to incorporation of dopant from dopant evaporation from the wafer, front side, back side, edges. Okay, so it's called auto-doping. I think we have this in for auto-doping. For example, auto-doping processes in epitaxial reactor. So you're running this process in a furnace, epitaxial furnace. Illustrated here are evaporation from number one wafer front side. Okay, number one wafer front side. Sebab this will be out diffused, and then you can actually auto-dope this, your front layer, or you can also auto-dope the neighboring substrate, neighboring film, because you have a gas stream coming in. So gas stream ni dia akan bawa, jadi carrier gas, dia akan bawa dopant evaporation, evaporated dopant if you like, into the atmosphere within the chamber, within the reactor, to auto-dope the next substrate. Okay, that's possible. From wafer front side, number one. Okay, from wafer back side or edges, it's also possible. You can dope to the side or to the edge. Okay, so you don't intend to dope, but then you dope due to auto-doping effect. From other wafers to other wafers. Macam ni, other wafers. From the susceptor. Susceptor ni holder dia. Possibilities to get your dopant from the susceptor as well, right? Concentration decreases with thickness because dopant has more film to diffuse through to enter gas phase. So this will not be as critical if you have a thick layer. It's about the possibility to happen very small, but then the possibility is there. But then if your film is very thick, high thickness, the impact will be way lower because the dopant yang you auto-dope tu, it has a bigger volume to cover. Okay, hence did not diffuse fluid, it will take some time and a big volume to cover. So as a result, the effect will be mass ataupun tak terlalu significant. On the other hand, if you're working on epitaxial layer, which is typically very thin, so if you have a considerable level of auto-doping, then you might change your epitaxial layer punya doping level, right? So if it's not that critical in the thick layer, if you talk about microns, then probably you will not be able to see this unless you do your characterization. For example, so we learn about characterization before. Remember SIMS? Anyone remember SIMS? SIM characterization? Concentration on the Y, concentration or whatever, dopant in this case, and then the depth into the sample on the X. When we talk about diffusion, right? We talk about diffusion junction profile. We talk about ECV. We talk about SIMS. SIMS is secondary ion mass spectroscopy, one characterization method that you can use in order to understand the profile of your dopant. Okay, for example, so dopant profile, katalah yang ni dopant profile, and then this is your background concentration, and this is your junction depth. Right, so you can study this, you can characterize this to see if you get auto doping in your film at all, right? So this will not be as critical if your film is very, very thick. If you talk about microns, then probably the auto doping will not be significant. But if you talk about epitaxial layer with a very thin thickness, okay, low thickness, like tens of nanometers perhaps, not even 100. So then the impact of the auto doping will be more significant. So if you talk about number one, for example, number one, if you relate back to this, number one is what? Wafer front side doping. Concentration decreases with thickness. Yeah, exactly the same thing. If you talk about 2 to 4, 2 is wafer backside, other wafers, and susceptor. Auto doping at constant level, but very low, right? Very low sebab dia jauh lah nak transfer, relatively harder to happen. But it's a lot easier to happen if you talk about front side dalam wafer sama, just the next layer, just in the neighboring layer. So the possibility of happening is higher, right? Out diffusion and auto doping. So last time when I was on my PhD, let me just share with you. So my PhD was on evaporated laser crystallized, evaporated is a bit, the title is a bit long. Evaporated laser crystallized. Evaporated laser crystallized silicon thin film solar cell on glass super straight. Ada kat depan tu light trapping, development of light trapping. Saya pernah lupa tajuk lah. That was 2016, 5-6 years ago. Development of light trapping. So I would like to relate to the out diffusion thing, right? Development of light trapping in evaporated laser crystallized silicon thin film solar cell on glass substrate. Panjang tajuk, eh? So the longer it is, the more specific it is, right? So it's about development of light trapping in evaporated. So I want to relate to what we learn now. Evaporated. So that means I evaporated silicon thin film on glass, and the film thickness was about 10 micron. To relate to the deposition thing and out diffusion. Okay. I deposited 10 micron of amorphous silicon on borosilicate glass, but in between there are interlayers of, we call it ono, oxide, silicon nitride, silicon oxide, followed by silicon nitride, followed by silicon oxide. Ono, silicon oxide followed by silicon nitride. Ada 3 layer lah, basically this interlayer. Oxide near the glass, and then nitride in between, and then another oxide near the silicon. So evaporated 10 micron of amorphous silicon, guna electron beam evaporation that we just learned in the previous topic. Then I obtained amorphous silicon, right? Amorphous silicon, but I wanted to get a polycrystalline. So how to get polycrystalline? I use laser crystallization. laser crystallization, hence the name inside the PhD, right? Evaporated laser crystallized. So that means amorphous silicon was laser crystallized. Guna laser tu you scan macam you scan kertas dekat scanner. Kan you nampak move kan. So the exact thing took place. Laser kita guna 808 nanometer IR laser continuous scan across the film. Then you akan dapat the moment you're doing the scanning, so the portion of the silicon film atau glass tu yang kita katalah ni laser beam saya scan across silicon film on the glass. So the tempat saya scan tu dia akan melt at 1400 degree Celsius. Remember we talk about Czochralski process, you melt the silicon. So in this process I use laser to melt. Pakai laser you melt, you do the melting on the glass. Maknanya amorphous silicon tu dia akan jadi liquid for a short time before it recrystallizes. Maknanya amorphous guna laser dia akan tukar jadi liquid silicon on the glass, tapi tak pergi mana duduk atas tu ya. But then it will be recrystallized through a recrystallization process. Dia akan recrystallize, dia akan jadi polycrystalline. So yang mana yang saya dah scan ni belakang ni semua jadi polycrystal. So yang depan ni dia akan melt, dia akan form polycrystal seed. Seed layer tu dia macam layer yang induce next crystallization lah. So that bila ada seed polycrystalline, the next layer yang you melt kat depan ni, dia akan follow crystallinity yang belakang. Dia akan follow. So as you scan, it will melt and then they will form nice polycrystalline silicon. Right. So how is it related to this particular section? Okay. What you can do in order to it can be good, it can be bad. You can actually dope. You can dope your oxide, nitride oxide. You can dope them before your silicon. Maksudnya saya start dengan glass, kemudian saya deposit interlayer yang oxide, nitride, oxide, kemudian saya evaporate amorphous silicon. So proses dia mula di bawah. Start off with bare glass, tak ada apa, cuci. Oxide, nitride, oxide, amorphous silicon. The amorphous silicon is not doped, maknanya the intrinsic silicon, but your oxide, nitride oxide can be doped beforehand. Kemudian when you do the laser crystallization, you melt, right? You melt the silicon. So due to the melting process, high temperature lah technically, you don't use the heat from furnace, tapi you pakai laser. So the laser melting will actually cause out diffusion of the dopant from the interlayers. Dia akan out diffuse masuk silicon and dope the silicon. Okay. So you can actually design this out diffusion as a desired process. Maknanya you boleh design lah. Ataupun you can just acknowledge that there is out diffusion of certain dopants from the layers. Okay. Dia boleh jadi secara tak sengaja ataupun dia boleh jadi by design. So in this case, we design the out diffusion process from the interlayers during the laser melting process, laser crystallization. So during the melting, the dopant will out diffuse from the interlayers going into the silicon and dope the silicon at our intended level. Okay, apa yang kita nak, right? So this is what it means, you know, bila you tahu the process, how to do it, how it happens, at what temperature, what causes it, what stops it from happening, you can use the process knowledge to your advantage. So that's the whole point. So you boleh avoid ataupun you boleh not introduce. Okay, certain things generally you want to avoid the defects, but in some cases you want to introduce defect for some reason. Okay, so this is about utilizing the knowledge that you have. Tak semestinya you guna out diffusion ni, you take it as a bad thing or bad scenario. You can use to your advantage, right? So that's the point. So bila you dah belajar semua proses ni, nanti you can just plug in, why don't we try this, why don't we combine with this, itu proses integration. Okay, bila you jadi proses integration engineer, then you have to know how do you incorporate litho, search and search with certain edge, with implant, without diffusion, but then with specific film deposition techniques to be able to produce your device. Okay, so that's about process integration, combining various knowledge, very fundamental from each process into a process flow to deliver your device. Right, CVD systems, It can be APCVD, LPCVD, PECVD, HD, high density plasma, HDP, HDP-CVD, high density plasma, LACVD, laser assisted, banyak proses, banyak CVD. So the basis is still CVD. But then you can have many things on the front of the name or the process name in order to get whatever you want. Okay, ada pun certain properties because every single process will give you different properties of the firms that you want. Okay, maybe certain properties or certain process is good for silicon but not good for ITO, not good enough perhaps. I don't know, maybe certain process is very good for ITO but it's not good for silicon, or it's good for ITO but not good for silicon dioxide, right? Ataupun you can just use the very same platform PACVD for silicon oxide, for silicon nitride, by just changing the gas. Tukar nitrogen, tukar oxygen, you still have your silane there to give you silicon, but then you combine with oxygen, combine with nitrogen in the very same chamber. I mean, you arrange in sequence lah. Maksudnya kalau, for example, if you go back to my PhDs now, silicon, then you have interlayers, yang tiga tu ono layer, oxide, nitride, oxide. You can do this ono, you can deposit this ono layers in PECVD, right? Oxide first, followed by nitride, then oxide, without breaking the vacuum. Without breaking the vacuum here means you can retain the vacuum condition dalam chamber. You just introduce different gases at different times. So in this case, you start off with silane dengan oxygen to get silicon dioxide, and then you shut off oxygen, you turn on nitrogen, and you're going to get silicon nitride, for example. And then you turn off nitrogen, turn on oxygen, and you're going to get oxide. Okay, so yeah, that can be done. You can actually do that in the very same process. And you can also, kalau you tak pakai ono, you tak buat ono yang dalam CVD, you can also use RS sputtering. Ni nak combine knowledge, combine knowledge. You can sputter silicon dioxide first, and then you can sputter silicon nitride, and then you can sputter silicon dioxide again, one after another. Or you can also do reactive sputtering. Okay, macam tadi saya cakap, reactive sputtering. You can use silicon target. Kemudian bila you buat oxide deposition, you can just inject oxygen to get silicon dioxide. And then shut off oxygen, you turn on nitrogen to get silicon nitride. And you turn off nitrogen, turn on oxygen to get silicon dioxide. So you can define all these process steps in the very same process recipe. Satu recipe, you can define layer by layer sequentially, right? So that's how you play with the process knowledge. So in this case, you can RS sputter, you can oxide, you can oxide, but you can do PECVD, or you can explore other type of CVD in order to do this ono deposition. Okay, so it's very flexible in that sense, as long as you know what do you have in every process, what are the capabilities of the process. Okay, so if we talk about CVD reactors or configuration, so we typically call this as configuration. It can either be horizontal, it can also be vertical. Horizontal boleh, vertical boleh. Okay, so you can mount this horizontal. That means your wafers are mounted horizontally. Your wafers can also be mounted vertically. Okay, so that will affect the thermodynamic of the process. Sebab you kalau mount different way, then the reaction, surface reaction, the gas flow, the ambient will change, and that will eventually affect your throughput, for example, and that will also affect the quality of the film. Okay, and in fact, if you talk about the throughput and the quality of the film, this is not always true because you can do something on top of the current configuration to change or to solve the problem. Okay, you boleh guna horizontal, but then you can solve throughput by some other properties of the chamber. Boleh juga buat. So this is not always true. Saya just bagi tahu you some basic ya. Tapi with the advancement of the equipment manufacturing, you can solve many things. You can probably manufacture equipment, CVD reactors with horizontal configuration but high throughput. That is also possible. It's just too many to state. Tapi ni is the conventional or fundamental knowledge. Tapi if you look at the current equipment, for example, if you explore LAM Research, LAM Research is a new company just started, I think last year or so in Batu Kawan. LAM is a company which manufactures fabrication equipment. Dia tolong buat equipment untuk front end fabrication. Untuk Silterra, untuk Infineon, untuk Onsemi, untuk Osram perhaps. So dekat Batu Kawan baru buka je. You can just search online. I'm not sure if they offer internship as well. Tapi kalau you join company ni, you will be learning a lot on how do you manufacture a fabrication equipment. Deposition ke. Dia ada banyak lah range of processes yang dia boleh cover. So you will learn from ground zero lah. How do you manufacture or build an equipment to deliver certain process capabilities. Nak buat chamber macam mana, nak buat vacuum system, nak combine vacuum level macam mana, flow rate, liquid precursor ke, gas ke, injector ke, coil, whatever, heating system. Kalau you join company ni, then you will do, if you're very hands-on on equipment and repair, everything, try to explore this, LAM research. You dah ada process knowledge, you dah ada fundamental on the physics. Now, how do you use equipment assembly or build up in order to deliver those physics? That will be very, very on high demand. Check out LAM dekat Batu Kawan. LAM research. Saya nampak multiple vacancies last time. Looking for material science, physics, engineering background. Okay, so LAM research. You are building equipment from ground zero. So this one is more on the it's actually, sorry, this is my LP. This is APCVD. Or wrong. APCVD. This is very unique to APCVD, which requires surface reaction, a limited region at low temperature but at high growth velocity. You can go back to this curve. Yeah, this curve, growth. Yeah, growth rate versus temperature. Okay, and this curve you can always relate to the every system. Okay, every system is unique. So see temperature and growth rate, velocity rate. So how do you find the sweet spot? Sweet spot mean optimum point. Kadang-kadang you dapat something, a curve like, for example, like that. Like that. Okay, kat sini dia naik, sini dia saturate. Sini kadang-kadang you dapat something like that. Plateau here. Okay. By the time kita boleh swing curve, ada tu swing curve untuk lithography tu, right? To choose the best CD at the lowest point during your test one, right? Test one. So this is very unique to APCVD. I'm not going to cover in details. So this one is LP CVD. Oh, sorry. Yeah, LP CVD. In terms of the growth velocity and the temperature, it's very unique. Sorry. This one is same thing. Temperature and deposition rate is very unique to the system. Right. So this is an example of PECVD. So PECVD is plasma enhanced CVD. So you use plasma to enhance the CVD process. So the key is still CVD, but the rate is enhanced by plasma enhanced CVD. So if you look at the configuration, it looks pretty much similar to what we discussed during sputtering. Okay, nampak ada plasma kat tengah, and then you have two electrodes, counter electrode, opposite polarity, and then you have gas inlet for silane and O2, and then you have connection to the pump, and then you have the grounding and the voltage to be able to form plasma. So the whole thing is still like the plasma system. It involves bombardment of energetic ions from the plasma, and when you have this capability, plasma enhanced, you have an option to reduce the temperature, low temperature, because in essence, if you talk about CVD, it has to involve thermal decomposition, and to be able to have thermal decomposition, you need to have the thermal component, heat component, high temperature component, which is able to decompose. Okay, tapi bila you ada plasma, that will do the part partially. Okay, plasma tu dia akan enhance the decomposition, and as a result, the system doesn't need to run at a very high temperature. So perhaps if you run a typical CVD, you used to run at 1000 degrees C, perhaps, right? 1000 degrees C. So with plasma enhanced, since you already have the plasma in the process, in the system, which will enhance the decomposition already, so you then have an option to reduce the deposition temperature. So bila you ada plasma, you ada low temperature, you can then regulate or you can then optimize these two parameters in order to produce the intended properties of your deposited layer. Okay, so the plasma will enhance the decomposition mechanism of the incoming gas, saline in this case, and you have an option to reduce temperature, which you don't have if you don't have plasma. You have to run at high temperature in the region of 1000 degrees C plus minus in order to initiate the decomposition. So this is another one, high density plasma. Plasma juga, but then it's high density. So to be able to have this kind of plasma, you need to use microwave supply 2.4 gigahertz. Generate high density plasma. The rest are pretty much the same. So high density plasma, microwave supply. So you have RF supply as well, just like the way we run RF sputtering, 13.5, 6 megahertz. So that will require your LC network, macam RF system juga. But the rest are the same. Chamber, electrodes, inlet. Okay. So with high density plasma, you may also introduce bias. With high density plasma, it's plasma enhanced, just like PECVD, cuma the density dia lagi tinggi. You can even reduce the temperature to lower temperature. Kalau tadi was like 200, 300, 300, now you can reduce to 150 and still has CVD going on, right? So just imagine you started off with 1000 degrees C, conventional CVD, you use plasma, you can reduce to 200 to 300. You use high density plasma to even enhance the process. So you ada window untuk reduce, you dah enhance. So the decomposition is enhanced. So you have the option to reduce temperature. So that's how you play. The moment you have plasma, you can reduce temperature. If you don't have plasma, you have to increase temperature. Else, you won't have CVD, right? Simultaneous sputtering of film with deposition result in denser planarized these properties of the film deposited. Okay. This is laser assisted LACVD. You can read later on. I don't want to go through. So you basically use laser untuk replace plasma. Okay. So use laser to target laser beam. You target the area to be deposited. Okay, you treat dengan laser at certain temperature, and then you're gonna have LACVD. LA ni tak common, because you use a laser. Laser means it's a bit expensive. Almost done. Yeah, almost done. Step coverage, mean free path. Lambda kita dah discuss. If you have low vacuum, then you have longer mean free path. If you have not so low vacuum, maksudnya in the region of 10 minus 1, say, then 0, then your MFP will be very small. Okay. So high pressure, like the best word to say is pressure. Kalau high pressure means high, close to atmospheric, then small MFP or small mean free path, lambda. If you have low pressure, then higher lambda, right? So if you want to have a more isotropic distribution, uniform, you need to go for low vacuum. Uniform low vacuum. So yeah, but doesn't mean low vacuum is always good. It depends. Just like what we did last time when I was in Fuji Electric. Certain process parameters requires you to run at high pressure to introduce some roughness, and that will help to improve certain process parameters. And process parameters ni, it really depends on what sort of devices are you working on. Kalau transistor, then a set of parameters, solar cell, a set of different parameters, SSD, a set of different parameters. So you really have to go and have a look at the set parameters that you want to produce, and then you go back to the process, customize the process to be able to get the optimum set of parameters intended. Conformal coverage, equal film thickness over all substrate topology, especially if you want to deposit over features. You want to have something like that, ideally, but you'll probably end up with something like that. Okay. tak conformal lah. Certain, if you look at this sketch, the second one, tengok dekat edge ni what happened. It breaks at this edge. Macam ada seorang student saya tu dia buat MSc sekarang. They try to deposit ni piramid lah, silicon pyramid. So what he's trying to do is he's trying to spin coating, macam litho punya resist coating. Try to spin coat a very thin layer of organic material, PSS. Organic polymer P-type. Organic tapi P-type material. So your silicon here will be N-type, your P-dot will be P-type. If you have a conformal deposition on the pyramid, then that will mean that you're going to have your P-N junction. So your P-dot here will be P-type, your silicon side will be N-type. So P sitting on N. So you have your heterojunction lah. Heterojunction P-dot on silicon. But at some condition, at some deposition condition, bila spin coat, you'll probably have something like that. It's very thick like that, and then at the apex of the pyramid, it's very thin, or it even breaks. It even pecah. Sorry. Ini tebal, ini nipis. Tebal, nipis. So if you want to form a P-N junction, in this case, your wafer is N-type, your pyramid is N-type, and your P-dot is P-type. So that means your junction is not continuous. I need the real issue that I would like to share. Okay, real issue in the real research atau manufacturing. Bila spin coat or you run other processor pun sama, if you have features existing below, existing features, square ke, pyramid ke, nanowire ke, nanorod ke, porous ke, whatever. So you will suffer from this condition if you don't optimize your process properly. So in this case, we want to have a continuous P-N junction, but in some condition, your P-type breaks dekat puncak ni, dekat apex, dekat summit. So bila dia break, that means you ada P-N junction kat sini. Tapi you tak ada P-N junction kat sana sebab dia pecah. So there's no P on N on the top. Tapi you ada balik kat sini P-N junction, P on N. Kat sana dia pecah balik. Sini you ada balik P on N. So you have P-N junction. So your P-N junction is not continuous. And to relate this back to 386 last time, kita discuss on lateral conduction, right? You want to extract carriers on all the places across the surface. So just imagine if you put this into a device. Kalau you ada metal contact kat sini, metal contact to extract carrier from the apex, from the summit, and metal contact on the other side to extract carriers from the rear side. So the rear side tadi issue lah sebab dia flat. Tapi front side, bila you nak, kalau you punya metal contact sits on valley, dekat valley punya area, there's no issue because the P-N junction is there. So carrier separation will be effective there. We learned about carrier separation, right? Electrons will go into N-type, holes will go into P-type, and then you collect them in outer circuit and you get your source cell, for example. Tapi if you deposit your metal on the broken area, you tak ada junction kat situ. So you are putting your metal sitting on N-type and it will short the junction. So this is where you get short circuit. You don't want to have short circuit because your metal is sitting on the opposite polarity. It's supposed to sit on P-type, but it's now sitting on N-type. Sebab dia tak ada P-type, so P-type pecah. Then your metal is sitting right on the N-type silicon. Tak ada junction, right? So bila tak ada junction, then you have a problem. There is short circuit. So coming back to this conformality and step coverage, so it's not only limited to the CVD, PVD. Of course, CVD is the best of all, but then under certain condition, or if your slope is too steep, like that, or if you have nano wires to cover, it's very, very difficult. Okay, walaupun you pakai CVD, that could help, of course, but then to cover nano wires with CVD is equally challenging, even though CVD is the best of all if you compare to sputtering evaporation. Evaporation, of course, is the worst. Okay, it's not only limited to PVD. CVD is also applicable to spin coating if you have this step coverage issue. Okay, so conformal coverage, certificate, non-conformal, all the stuff. But of course, you can If you talk about CVD, PVD, you can do rotation, you can do heating, you can do annealing after the process, and you can even do a high temperature treatment or heat assisted process after your spin coating of PDOT or whatever. Can also be done. So that's step coverage issue. Okay, this is another illustration of step coverage. You want to get something like that, but you'll probably get something like this or something like that, even worse. You block the incoming firms or incoming atoms or molecules to be deposited because you close the channel for deposition. Okay, so we learned about aspect ratio last time. Okay, height over width. So when we talk about RIE, deep etching, okay, DRIE, to put it isotropic, so it'll be very challenging. So certain parameters can help, like rotation and heat and yep, but then it can still be challenging for even CVD, right? Yeah, I think we've done for the process. So we've done the CVD. Is it okay so far? Kalau interested, try tengok lab research. If you're not interested so much on the process, but you are more interested on the equipment side, you minat nak install vacuum pump ke, atau you minat nak buat automation ke, nak buat robot teaching ke, nak handle sensors, and you're on the circuitry, pandai baca circuit diagram, right, then you can apply for equipment manufacturer, macam lamp research. Okay, macam lamp. So any question on CVD? So we have completed PVD and CVD. So on Monday, we'll move on to process integration, where you combine all the processes that you've learned before to fabricate IC, or integrated circuit. Tapi you can use the very same knowledge, the very same process to fabricate some other stuff as well. And the process integration knowledge will be useful when you do the presentation later on, because I'm going to teach you daripada wafer kosong, first step, second step, sampai you complete the device. Okay, what do you combine? What comes first? What comes second? What's next? Why is it so? How do you do the masking? How do you etch? Where do you etch? Why is it like that? All the stuff will be taught in process integration. Dan you boleh guna the same knowledge untuk buat process integration of other devices, solar cell, LEDs, SSDs, whatever lah yang ada dalam industri kat sini. You can just use certain process then atur accordingly. Then bila you atur tu dia macam flowchart lah. Flowchart tu, the process tu will actually represent a process flow of your device fabrication. Okay, process flow tu is actually your sequence in the device fabrication, and itulah kerja process integration engineer. Okay, they can oversee the whole process since day one sampai habis. What goes wrong with certain process? Why is it so? How to solve? How to improve process number 35, for example, to be able to deliver certain output characteristics. Okay, so done. Any questions? Nope. All good. Kalau tak ada soalan, I'll see you next week. Inshallah, we'll talk about process integration. Okay. Bye-bye. Take care. Assalamualaikum.